بسم الله الرحمن الرحيم ولا حول ولا قوة إلا بالله العلي العظيم. Last session we talked about dexterity and the measure of dexterity in terms of Jacobian transpose. Jacobian transpose give a map or a relation between the two norm of Q dot in joint space with respect to the task space. And we show that JJ transpose inverse, regardless of the size of J, which could be a square matrix, it could be a fat or a tall matrix. JJ transpose is a square matrix, always square, and it has always determinant and eigenvalues. So the JJ transpose inverse will propose a sphere in the joint space into an ellipsoid, into the task space. And this will provide different physical properties to the action or the relation that we can have in our end effector and in the task space speeds. So we showed also that we have two types of extreme values. One extreme value is that this ellipsoid that we show here, this ellipsoid becomes a cylinder. One of the eigenvalues is equal to 0 if the determinant of the JJ transpose is determined by the multiplication of the eigenvalues of the JJ transpose. If either of them is equal to 0, then the determinant is equal to 0, and the inverse map, as we see here, becomes singular. So we have singularity in that specific direction that the eigenvalue, the eigenvector of that eigenvalues, which is equal to 0. So now the eigenvalues and the eigenvectors come into the picture with a more physical concept. Otherwise, this is usually not a good value, because in that direction we cannot get the inverse and we cannot have a motion. A very small motion at this direction, if we would like to reach, cannot be reached by finite value for the Q dot, and Q dot goes to infinity. Or actually we are on the boundary of the workspace and we cannot move forward. This is the close relation that these two particular cases they had. But in the other side, we have isotropia as a good characteristic of the Jacobian. Isotropy is when this JJ transpose is equal to unity, is equal to 1. And this means that all the eigenvalues are equal to 1, not close to 0, and not even different. They are exactly equal to 1. This means that this sphere in joint space will transform into another sphere, exactly a sphere in the task space. And this means that we can have different direction in the velocity direction quite easily by the action that we can have in the joint space. So isotropy could be a measure of how well a robot is designed and how well we are far from the singularity of these extreme cases. Now, going a bit in detail and quantitatively, let's see what would be the relation between Q dot and X dot. What would be the maximum value of this ellipsoid and the minimum value of this ellipsoid? These are also related to the eigenvalues. And we can see that since the determinant is equal to determinant of J transpose is equal to lambda 1 to lambda n, this relation is somehow the inverse of this determinant, and we can consider that by a singular value of J. We have the determinant of or eigenvalues of JJ transpose, but in linear algebra, there are the determinant of JJ transpose are related to the singular value of J that can be easily found by MATLAB and other software toolbox by the square root of the eigenvalues of JJ transpose. So instead of having a JJ transpose, a squared matrix, which is dimensionally also squared, we can use their own particular Jacobian, which could be non-square, it could be a square matrix, it could be a fat or a tall matrix. And then if we use the singular value here, this singular value is actually the square root of the lambdas. So if we have this in mind, we can define the first manipulability measure, a measure of how well the robot is designed in terms of the Jacobian. The manipulability measure mu is defined by the multiplication of the singular values of J. This is in short, or the multiplication of the eigenvalues of JJ transpose, square root of that. These two are actually the same, and this gives us a proposition or a property of the design of the manipulator, when if mu goes to 0, if this particular measure goes to 0, this means that at least one of the lambdas are becoming to 0, and we are going to some singular configuration. And if mu tends to 1, we are getting to the isotropy case, where all the lambdas or the sigmas are equal to 1. So we have these two extreme cases, and this is a singular one. This goes to isotropy, and usually we are something between these two values. When we go closer to the 0, we are getting close to singularity, and when we go close to 1, we go close to isotropy. And notice that for this particular measure, this could be even more than 1. Consider that all the eigenvalues or singular values are larger than 1, then we can get something larger than 1 as well. And this is not a non-dimensionalized measure. But the measure has the property that all the eigenvalues or all the singular values of the Jacobian is in considering into the mind. This particular slide gives some more detail on the quantitative measure that we can use by considering the mu factor here. And consider that the robot, we have different type of robot we can design in here, or we can have different lambdas or eigenvalues here. Consider a robot that is under-actuated. An under-actuated robot is a robot that the number of actuated joints are less than the degrees of freedom of the task space, or the Q space is smaller than the X space. So we consider that we have only one actuator or two actuators for 6 or 5 or 6 degree of freedom motion. We have limited actuated, we call it under-actuated, and in Farsi we call it furu tahrik. Furu tahrik or under-actuated is when the number of actuators is smaller than the number of the joint. If this is the case for sure, we have one of the lambdas equal to 0. We have not all the direction actuated, so mu is equal to 0. And this means that we cannot go to the certain direction, we cannot move to the certain direction, or the motion of the robot is not that easily plannable, and we cannot generate all the trajectories that we require. If the robot, on the other side, we have another particular robot which is very well designed, and we can see many of that type in the nature that are redundantly actuated. But redundantly actuator is the inverse. We have more actuator than we require. I will show you a number of examples here in a few slides, in a few next slides, that many robots, many creatures in the nature are usually the design of the God is somehow redundantly actuated. It means that if we need only 3 degrees of freedom, many natural or biomimic designs are having more than 3 actuators. Just consider your shoulder, for example. The shoulder has 3 degrees of freedom, but if you go through the design or the muscles that are used to move the shoulder, you see that there are 4 groups of muscles used in your shoulder. And this has some benefits. And why it has the benefit? Regarding the Jacobian, we can see that if the robot is redundantly actuated, we have some extra singular values. We had 3 degrees of freedom. This JJ transpose is 3 by 3, but we have 4 singular values. We have 1 or 2 depending on the degrees of redundantly actuated. We have some more degrees of freedom in terms of the actuator. And as we can see, the first benefit is that we can avoid reaching to singular point or trapping into the singular point. So the motion of the robot becomes much more singular free and much more better. In terms of quantitative case, we can say better. In terms of qualitative, we can say better. In the terms of quantitative measure, we can say that the manipulability measure becomes higher. It gets away from 0. Why? Because we have added another singular value to the system, which is usually non-zero. And note that all these are considered for a Jacobian, that the Jacobian is orientation or configuration dependent. In some cases, maybe in some particular motion posed, for example, here, we have some eigenvalues, in here we have something else. And if we have an extra sigma or an extra singular value in our system, then, or at 1 degree of freedom, more actuator in the system, we can increase the manipulability measure. Of course, it is expensive for industrial design or for mankind design. Having another actuator means you should pay for that actuator, and that's why many handmade robots are not redundantly actuated. But the good one, the one that you require some sort of manipulability, you need to have some speed or some sort of quickness in the robot. It is very good to add a redundantly actuated system. And if you again consider Cobra attack, as I showed you the movie last time, the Cobra goes to some configuration that the vertebra or the necks, the configuration of these bones, interconnecting bones, gives you more degree of freedom, not 6, more degree of freedom, 7, 8, or even maybe 14. 14 vertebrae will be working, or 14 actuators are working for a particular attack, which only needs maybe 6 degree of freedom. And this has been analyzed that the posture that a cobra will get before the attack is somehow optimal to increase the manipulability measure. Or the other movie that I showed you with the card player, the fingers are so fast, it means that the manipulability measure is somehow fast. And how we can say that it is fast, or what is the in terms of numbers, we can consider the singular values of this Jacobian matrix, the singular values. In short, if you don't want to go through the detail, in short, this is very important, please highlight that. We can say that the maximum speed that we can get, the maximum norm of speed that we can get in the task space is somehow 1 over the minimum singular value that we can get for the Jacobian, and this gives you in the direction of the Vmax, in the direction that this singular value is obtained. And the minimum one is 1 over maximum singular value of the Jacobian. So why this is the case? As you see, Q dot is equal to X transpose JJ transpose. So basically the norm of that could be smaller than the norm of this. JJ transpose comes to the inverse, and the norm of this is particularly defined by the manipulability measure, by the measure mu. This measure mu has some maximum or some minimum values, and this maximum and minimum values gives you the maximum and minimum values of to the x. Or what we showed in here, we have an ellipsoid, we have a maximum value or a minimum value. This maximum and minimum values goes to the maximum and minimum value for the singular value. But note that the inverse value that you use, since this is coming in the inverse, comes into the denominator, the minimum value of this gives you the maximum value for x, and the maximum value for sigma gives you the minimum value for that. We will use this relation quite extensively to find this ellipsoid shape in terms of simple manipulator. As you see, mu denotes the gain. This mu or the sigmas, as you show, gives you the gain that we can get between the speed of your actuator corresponding to the task space. And again, I remind you the card player that has very fast speed in the fingers, that you can don't notice the tricks that he is doing. This is because it has very fast speed at the fingers, and having very fast speed at the fingers means having a larger manipulability measure in the design of the hand. Of course, it has a lot of training as well to use that speed in the fingers. Again, if mu is equal to 0, we have in some direction the velocity is not attainable. We have singular value. And if mu is equal to 1, we have a uniform velocity. In all the direction we can have very uniform velocities at the output. And also the shape of the ellipsoid can show you very informative case. So in one direction, if we have very large speed. In one direction, we have smaller speed. In the other direction, we have a combination of this larger, the maximum value or the minimum value, something in between. And this means that sometimes singularity is not very bad. Maybe we have in some direction, we have singularities, as Zahra asked last time, but in the other direction, we have higher speed and better speed. And this means that we can consider that generally in terms of the ellipsoid. Although mu gives you a very global or something very general perspective of the dexterity, the ellipsoid can give you all the details that you can get in the direction of the velocities. All right, let me also add another basically another measure which is simpler and somehow maybe has the same, almost the same characteristic, but it is normalized, and this is somehow better in terms of mathematical representation, but it is not as informative as the manipulability measure. And this is also defined by the condition number of a matrix. Again, in linear algebra, condition number is defined and very, very suitably used in many calculations that we have. If we have a very large condition number, this means that the matrix is not very good in terms of inverting and getting inverse of that, as you see in linear algebra course. But what was the condition number? Do you remember? If you recall, the condition number of a matrix J, which we call it by kappa, is the maximum singular value. If it is squared, of course, the square root of eigenvalue, but usually we have maybe non-square, the maximum number of the maximum singular value divided by the minimum singular value. So it could be a large number, and if sigma min tends to 0, we have some singular cases, this will becomes very, very large. So something, this is a measure between 1 to infinity. If we use the inverse of the condition number, we call it arcant, and you can use arcant command in MATLAB or in many other softwares. Arcant gives you the inverse of the condition number, meaning that the sigma min over sigma max. Sigma min could be 0, so this is the limit could be equal to 0, and sigma max could be anything. And in particular case, if you see again, we have something non-dimensionalized, something between 0 and 1, very similar to mu. If arcant is equal to 0, this means that exactly like what we have in mu case in here, if arcant is equal to 0, at least one of the condition or singular values are equal to 0. So basically we are in singular configuration. And if arcant is equal to 1, all the eigenvalues are equal to 1. So we have an isotropic condition. And since we have a division of the maximum to the minimum, this particular condition measure or the condition number is between 0 and 1, and we can very easily find how close we are to the singular value, how close we are to the 0, or how close we are to the isotropic case, the good design, when we are close to 1. So I prefer arcant. And somehow myself, I use that many times in my design, in the manipulators that I have designed, because it gives you a non-dimensionalized case. But it is not all informative because it has only the sigma 1, the minimum and the maximum values within that. Although in this case, as you see, we have all the eigenvalues. Mu has all the singular values multiplied to each other. So it gives all the direction of the ellipsoid, but here we have only the maximum value to the minimum value, or the minimum value to the maximum value if we consider the archon in the case. In any case, of course, these are only two measures. We have manipulability measure, and we have also condition number measures. And if you look into the literature, you will find a large number of other measures available for considering the manipulability. All of them, maybe some of them are called dexterity measures, not manipulability. But they have all the same idea of the ellipsoid and what we consider that in this case. We will work on your project somehow, not on the assignment, but on the project. I will ask the TAs to give you some design procedure, how we can find a manipulator, how we can design the length of the manipulator somehow that we get a better manipulability measure in terms of archon or in terms of the mu case, in terms of kappa or in terms of the mu. And you notice that all of these are depending on the J, either this one or this one, and all the J is usually configuration dependent. This means that in some configuration we might have a good condition number, but in some other cases we have bad condition number. As you see, when you extend your hand and you want to open the curtain, it is very hard. This has a hard condition number when we have fully extended case, but when you are writing something or painting, you have a very good condition number. We are getting close to isotropy. So these are local measures. We call it local because depending on the position that you are, where you are located, then the condition number could be the manipulability measure, or the dexterity measure could be something between 0 to 1. We can have also global measures. If we integrate all these measures for the whole workspace of the robot, we can grid this and find different manipulability measure and then integrate sum of all of them and divide by the number of integration somehow. Then we can have a average global measure. We have a global measure which is somehow average. And you know that when you average something, you reduce the sharpness of that. So it is quite possible that something manipulator is singular in some particular case, but when you get the average, that singularity becomes smaller, the values become smaller, since there are some other points that we have no singularities. So by talking about that, we can consider that different values of different cases and different values of the manipulability measure can be calculated. If there is any question up to here, I would be more than happy to answer. Please just open your microphone and ask if there is any questions. All right, so let's talk a bit about some examples. This example gives you some values to that. And again, I used a biological example. Consider a 2R manipulator as before. We could have find the Jacobian. We had already find the Jacobian on also in 0 frame and in 2 frame, and we know that the frame of representation doesn't change the manipulability measure, the important or inherent characteristic of the system, we use the Jacobian defined in the second frame, which was much easier for our calculation here, which was like something like that. And as you saw before, this was singular when we were fully extended arm, or we have a retracted arm, a fully retracted arm. In both cases, that S2 is equal to 0 or pi. Just for now, forget about that. And we would like to see what would be a good design here. Is it better to have both this length equal to each other, or this is a bit longer than that, or this longer than that? And amazingly, if you watch through different people arm, this is very similar to the arm of a human being, as you see here. For usual mankind, if you see, regardless if they are very tall or very short, this two lengths, the ratio of these two lengths, the forearm and the arm and the hand, we can say sa'ed and bazu, these two, the relation of that for different people are almost the same. And you can examine into the literature that this ratio is about square 2 if you consider that 1, L2 equal to 1, L1 is a bit longer and is equal to 1.41 square root of 2. And it is amazing why this particular case. And it is very amazing that this will give you some. This is the only particular case that you can have isotropy in the design. You have some optimal design. So for now, consider that L1 is equal to square root of 2 and L2 is equal to 1. We don't know if this is good or bad. We will examine that. How we will examine? We find the Jacobian transpose. So we have this. We can use symbolic manipulator in MATLAB or Maple software that you are now familiar with that. Just to open a parenthesis here. You know, in our examples, in our assignment and in our project, you are encouraged to use MATLAB. It is not good to just do everything by hand, because it is not possible to do that by hand. And since we have a graduate course, some undergraduate students are used to just doing everything by hand. But in this course, you are not only allowed to use MATLAB, but you are encouraged to do that. And even in the exams, since we have, take-home exams, we have, the exams are not open book, they are open book, and you can also use computer in your exam. It is very good that you write your own programs and codes in MATLAB and also in Maple, as you saw in the previous TA session. You can use basically also the Maple, the symbolic manipulation, either in MATLAB or in Maple, that can be used even for your exam as well. So I encourage you to learn how to design, to write these codes in MATLAB and Maple. Okay. Closing the parentheses, going back to the example. So we have a Jacobian which is dependent on L1, L2, and also sine of theta, which is theta 2 here, and cosine of theta 2. We can find JJ transpose by symbolic manipulation, very easy. Of course, we can do it by hand as well. And we can find the determinant. We had already found the determinant there. For this case, for JJ transpose, the determinant will be equal to S2 squared. And this is the case for L1 equal to square root of 2 and L2 equal to 1. If L2 and L1 are different, so this would be somehow different. Of course, the determinant has some length in it, L1, L2 in here, but again, they had S2 as well. But here we consider only L1 equal to square root of 2 and L2 equal to 1. And now we would like to go to the manipulability measures. So we need to find the determinant and the eigenvalues and also some eigenvectors. I will talk about eigenvectors a bit further of this. We can find the eigenvalues. This is very hard to do it by hand, but very easy to do it by the symbolic manipulator. So you find the second order system and define the relation between here. The eigenvalues would be plus minus something, plus this, as you see, quite long. Can we have this design in some configuration? Can we have a theta 2 in some configuration that this becomes isotropic? You can see that only for this particular case, that lambda 2 is equal to 2, and lambda 1 is L1 is equal to square root of 2, and L2 is equal to 1. Then lambda 1 and lambda 2 can both become 1. And we have an isotropic. We have a very good design. Just for this particular bio-inspired design. And you see that this can happen if theta 2 is equal to 3 pi over 4. For a particular design, not for all configuration. As you know, this is configuration dependent. Cosine of theta will change and the lambdas are changing as well. And you know that if cosine of theta is equal to sine of theta is equal to 0, we are getting into the singular configuration. But there are some cases that if theta 2 is equal to 3 pi over 4, positive or negative, doesn't matter, then we have a singular configuration. And it is amazing. This singular configuration is within the workspace that you usually use your hand for writing, for painting, for what a human being is designed to do that, is up to do that. And the design is optimal. Why optimal? Because it is isotropic at this particular case. Of course, if you find a other position or another orientation, this won't be quite optimal. So this is the case that we can see. Okay, we can learn something from the nature and the very, very specific design of God that is specifically interesting to us. Now, consider that for this particular case, of course, with this angle 3 pi over 4, we are in configuration where we are isotropic when theta 2 is equal to 0. Or theta 2 is equal to 180 degree, we have a singular configuration, as we know that this was the case that we considered before. Now consider another angle, not the isotropy one, the best one, or the worst one, the 0 or 150 degree. Consider 90 degree here. Consider that these two arms are perpendicular to each other, and we consider theta 2 is equal pi over 2. What will happen there? What would be the speed? I would like to write to you how you can determine and find this ellipsoid relation in here. Very good. Okay, if theta 2 is equal pi over 2, for this particular configuration, then JJ transpose is very similar to 2 and square root of 2 here. You can find the inverse of that here. So we have both the Jacobian transpose and the inverse. And for Jacobian transpose, as we talked before, you can find the eigenvalues and the eigenvectors. Eigenvectors is 1, 1, 45 degrees, minus 1, 1, 135 degrees, or 3 pi over 4. So, of course, with the 1 over square root of 2 to have that. These eigenvalues and these eigenvectors can be used for finding the gains here. As you see here, I would like to use this one, or I would like to prove this one in this particular case. What is the maximum speed we can get? Does it relate to the, if we have a uniform speed at Q1 for sigma 1, sigma max and sigma min? We will discuss it in here quite easily, one by one, and we can see that this general formulation is quite true. Now look at this. You can see that, as you see, the eigenvalues for J transpose is 3.4 and I make it black. I will use the black one in further. But usually, as you see here, as you saw in here, J transpose inverse will give you the relation between Q to that. Here it is also very easy to find J transpose inverse. J transpose inverse is that, and we have also the eigenvalues find by that. It is not required to find both of them. If you have this one, J transpose inverse, the values will be the inverse of that. So if we have 3.4 here, we got something about about 0.3, and 0.5 here, we got something about 1.7. All right, so you don't need to find both of them. If you have one of them, of course, the inverse can be found quite easily. And what about the eigenvectors? The eigenvectors are also the same. So it is usually sufficient to find that, or to that, and it is much easier to find that in practice, because you don't need to first make the inverse and find that. And we have the eigenvalues and the eigenvectors. Eigenvector, again, 1, 1, and minus 1 and 1, as you see in these two directions. So for J, since we have this, we have singular values of J as well. So we can say that the singular values of J transpose is this, and for J, J min, and J max, as you remember this equation, we have singular value 1 over J min, 1 over J max as the largest gain and the smallest gain in here. Here we find that the largest singular value of J, again, it is a square root of the eigenvalues, but you can find it by MATLAB directly or finding by it here. Square root of the 1 over lambda max would be 0.54, and 1 over lambda min would be 1.3. And what about the direction? The directions are V min, the smallest one, 1, 1, goes to the maximum largest eigenvalues, and the Vmax goes to the minimum eigenvalue. So because it is the inverse one, so we have these two directions here. The gains are the reciprocals of the J singular values, and the directions can be found by the eigenvalues of J transpose. So by doing that, we can have everything in mind. I will prove that here. You never need to do the proof yourself. You can always use the final solution here, but notice that this is the proof of the mapping gain for that angle. So if we have this eigenvalue here, we have JJ inverse here. As you see, JJ inverse is in here given by this one. So the relation between norm of Q and norm of X, as you see, norm of Q is theta 1 plus theta 2, and JJ transpose inverse, we have it here, we put on here, we get to this point. So this means that Vx and Vy are related to theta 1 and theta 2 by these two relations. Can we use the eigenvectors to find that? Of course, we can use the eigenvector 1. You see here, 1 square root of 2, multiplied by lambda 1, eigenvector 1, lambda 2, eigenvector 2, lambda 2, eigenvector 2. This relation can be found by that, because we know in the linear algebra that all vectors are linear combination of the eigenvectors that we have in here. And these two values are nothing but lambda 1 and lambda 2 of JJ transpose inverse, which was the inverse of the lambda 1 and lambda 2 of JJ transpose. Now, what would be the maximum value or the minimum value? We can show in here, since we have here eigenvector 1 and eigenvector 2, this we call it V min here, and this we call it V max. We can see that if V1 is equal, if the direction that we are moving our hand, if Vx is equal to Vy, if in the task space we have a particular direction that Vx is equal to Vx1 is equal to Vx2, this is in this direction, so this becomes 0. Theta dot 1 plus theta 2 becomes something like that, which is square root of Vx2. We have this relation just by multiplication, just bringing this the other one. As you see, 2.9 now gives you 3.4 as we had before in here. We have a square root of 2, just dividing by that, you can find the maximum of sigma chi dot or x dot, Vx dot, which is basically the Vx1 and Vx2 square, would be the value that you divide this by square root of that. This is squared value, just make the square root of that, and you can see that this is equal to 1.541 q dot, as you had it here. Sigma max is here. You can see that this relation can be found easily by just the singular value relation. And the same thing can go for the minimum value velocity. For the minimum value velocity, this should be equal to 0. We know that this maximum will happen in 1 direction, and this will happen in 1 minus 1 direction, exactly at the same value that we can find in here. Look into do the manipulation by hand, but you can see that you don't require to do all this hassle of calculation. You can find just the G max and G min here with the V max and V min here, which are the eigenvectors here that you can see. And here gives the very, very nice final solution geometrically or graphically, that you can see if you have a square, a sphere or a circle value in the 2D space, as you see here, this will be changing in the task space to ellipse. Not ellipsoid, exactly ellipse, because it's a two-dimensional case, in two directions. The directions that you are the eigenvectors, the eigenvector 1 minus 1 and 1, and eigenvector 1 and 1. And remember, you have the inverse always in the case that you have in here. You can see in here, you have the inverse. So this becomes V min, and this becomes V max. The maximum singular value of JJ transpose give you the minimum direction of the minimum gain. The minimum gain is 0.451 as we had before, and the maximum 1.37. That can be easily found by the singular values of the Jacobian matrix J directly. You don't need to find J transpose, JJ transpose. You don't need to find the inverse. You don't need to find all this hassle of calculation. I have done it once to prove that this is correct, but you can see that you can simply find the direction, the eigenvectors, and the eigenvalues that you can find from the eigenvalues, you can find the singular value and you can find the maximum or minimum manipulability case here. Now, in terms of the measure, is it good if we are in 90 degrees for theta 2 is equal to 90 degrees? Are we close to singularity or are we close to the isotropy? This is something in between. You can see that lambda 1 times lambda 2 becomes square root of 2. It is not 0 and it is also not 1. And the non-dimensionalized case, our sigma min over sigma max is equal to 0.4, which is not close to isotropy and also not very close to singularity. This is some middle space that you can find in here, that you find the direction in there. So there are a lot of calculations here. I don't want to, bother you with all this calculation. More than that, I would like to give you the direction that you have this ellipsoid being comes into the picture. Is there any questions up to here? Okay, before going ahead, I would like to ask everybody about the time of the classroom. The time of the classroom in the month of Ramadan is quite very early. Of course, I am happy with that. I have no problem with that time. But I would like to know if you prefer to change the time of the class, and if it is better for you to change the time of the class, if it helps you to get more awake and being with us up from the beginning to up to here. I didn't have any feedback from you. Let me talk in Farsi here. از اول صبح تا حالا هیچ سوالی، هیچ ریاکشنی نداشتیم که خوبه بده، حداقل یه چیزی بنویسید من ببینم شما هستین یا نه. میخواستم بگم که ساعت کلاس رو اگر همه علاقه‌مند باشن میتونیم تغییر بدیم به یه ساعت دیگه ای که براتون بهتر باشه. اگر این ساعت مناسب نیست، البته میدونید که مشکله، چون کلاس های دیگه ای دارید و طیف وسیعی ما توی کلاس داریم. من دانشجو کارشناسی داریم تا دانشجو دکترا، بنابراین ممکنه این امکان پذیر نباشه. اما اگر من میتونم، پیشنهادی که میتونم بدم اینه که کلاس رو به جای ساعت 7:30 صبح مثلا ساعت 11:30 ظهر برگزار کنیم تا 1 تا قبل از اذان. My proposition if we want to change the class hours, change it to 11:30 Tehran time to 1 o'clock before the Salah time, before the Azan. So please give me some indication that you are available. Do you hear me and you have any connection with me? Just let me know if that time, because there is no class at that time and the only time we can change would be something like that. 11:30 to 11:30 to 12. And I would like to ask everybody if each of you give the indication. If one doesn't prefer that, then we can have that one. دینامیک توی این تایم 10:30 تا 12 روزای یکشنبه و سه‌شنبه. 11:30 تقریبا تموم شده دیگه. من از این بابت گفتم میتونیم بذاریم 11:45 دقیقه. اینم شدنیه. اگر کسی مشکلی داره لطفاً بنویسه تا پایان کلاس من بتونیم تنظیم بکنیم. یکی دیگه از بچه هم داره میگه که تو این ساعت کلاس دارن. I will prefer this one 11:45 to 13:15 Sunday and Tuesdays. خواهش میکنم نظر مثبت و منفیتون رو اینجا بنویسید، مثبت یا منفی. اگه منفی بود یه نفرم مشکل داشته باشه ما تو همین ساعت موجود ناچاریم ادامه بدیم. حقیقتی ساعتهای دیگه هم خیلی نزدیک افطار بشه، من چون خیلی صبح زود پا میشم و خیلی برام سخت خواهد بود که ادامه بدم. اگر مشکلی نباشه که همین ساعت ادامه میدیم. خواهش میکنم نظر بدید و بعد حالا در پایان جمع بندیم. در این حال دوست داشتم که صحبت‌های شما رو داشته باشم. فعلا 2 نفر مثبت داریم تا از 14 نفر. حسین هم مثبت 3 4. حسین مزه. We can fix the time Hussein, we can have the classroom at this time if everybody will consider that. Okay. I prefer morning. حسین علاقمند به ظهر نیست چون کارهای دیگه داره قطعا. Okay, let's we go further now and then we can see how we can go with that. Now that we have defined the Jacobian characteristics, the dexterity, the isotropia, and the condition number, we can go to the very interesting last part, the inverse solution of the problem, which is basically finding this inverse map. And it is very important. The Jacobian not only reveals the velocity map, but also the torque or the wrench map, not only the twist map, better to say not velocity because we have a 6 degree of freedom velocity, and we have a 6 degree of freedom force and torque map. And we have 3 different type of Jacobians and 3 different solutions in here. This is an advanced part of the course, so please be with me. You know, finding a Jacobian is usually very simple, but working with the Jacobian, optimizing the Jacobian, and finding the inverse is something else, which is more sophisticated. Of course, what we have in forward kinematic was like that. The forward kinematic was quite easy, but the inverse would have more calculations. Here, of course, it is much easier than the kinematic. The Jacobian inverse is easier, but you need to know some matrix manipulation and linear algebra, revealing the linear algebra here. Look at in here. We have 3 different type of solutions and different type of Jacobians. The first one is the simplest one. The most simple one is when the Jacobian is squared. We have the same number of actuators as the same number of degrees of motion. Q and X are all both equal to each other. In general, they are both M is equal to N is equal to 6. We call M the number of the actuators and N the number of degrees of freedom, which is always usual to 6 in general manipulators. Now, if this is the case, the inverse solution is very simple. You just need to find the inverse of the Jacobian, and this exists at non-singular. If determinant is not 0, if we are non-singular, then this is quite easily. You can find Q dot by the inverse of Jacobian, and you can find the force which is exerted to the environment by the inverse of the Jacobian transpose times the tau. And require and consider that. Now you can find 2 very important physical concepts, not at the singularities, but as the student asked you last time, even close to singularities, even when we are near singular configuration. if we are near singular configuration, to achieve when this is the case, then this Jacobian becomes infinity, you know, because the determinant becomes 0, the inverse doesn't exist. Don't say about Jacobian, to write the singularity, just even near singularity. If we are near singularity, this becomes very large. This means that to achieve a finite velocity x dot, you can see in some simple direction, you are very close to the boundary of the workspace, and you would like to go a bit further. You want to go very small in this case. You need very large speed at your joints. If x dot, to have a very simple or finite degree of x dot, since this is very large, you need very large joint velocities. And at singular point, this goes to infinity, so we cannot go further. This means that we cannot move at this direction. Which direction? We talked before now. We have the ellipsoids now. The direction that was identified by the eigenvector of that particular singular value, which is equal to 0. But in this term, what does that mean? This is also very, very interesting. This is very bad, but this is very good. Very large forces, these very large forces could be applied to the environment with low actuator torques. Again, if J is singular, J transpose is singular as well. Notice that J and J transpose have the same singular values. They have the same eigenvalues. So when this becomes singular, this is also singular. This means that very large forces could be applied to the environment with low actuated torques. This is the same, the weightlift athletes that I show you in a few number of points. I guess you can remember that. I don't know where, yeah, here you can see. Here you can see that both these two are good. Both two are good. You know, at a singular point, very large forces, F, can be held by small number of taus actuators that you can say. So we are in the singular point, we can have large point. What about this? This means that at a singular point we cannot move a bit forward. We are not possible to go that way. So in twist version, we have limitation in the speed or in the motion. In force or in wrench version, we can handle very large speeds. Very large forces could be applied to the environment with low actuator torques. And the story is finished for n by n because we don't need any different difficult inverse calculations because we have a simple matrix and we can find the inverse of the matrix by numerous calculation ways. Now go to the two other topics. These are more important for us, and these are more advanced, basically. First, inverse solution for under-actuated robot. The under-actuated robot, which means that we have the number of actuators are smaller than 6. Consider a 6 degree of freedom robot, and only 4 actuators. Why we do that? Usually because we don't want to spend less money for that. Do we have this in nature? Yes, we do. In some particular other cases. Of course, in nature, usually we have the other case redundantly actuated, but this is also available. We can look into the nature, especially in insects. In insects, the actuators are very limited, but they can move quite well. and everybody knows about Susk. Susk is very, it has some sort of the way the different legs of an insect can work is somehow under-actuated. But in case, don't go about extra material, go to the detail of the mathematics that we would like to see in here. So what we can say is inverse solution for that is different. So we have the solution, we have what we call, consider that we have only solutions, we don't have a lot of solution or one solution. Usually the Jacobian is basically singular. We cannot find the inverse quite easily, and the Jacobian matrix is a tall rectangular, is somehow the number of the rows are larger than the number of the columns, because each actuator will add us a column, and you remember each column of that was a screw axis, and the screw axis was related to the actuator. So we don't have a square matrix, we have a tall matrix, and usually there is not an exact solution available. Only the solution is available when x dot lies in the range space of the Jacobian. So we can move only in the direction which is in the range of the Jacobian, or tau lies in the range space of J transpose. We cannot exert all the forces in the direction that we would like to know. We can only exert some forces which are basically in the range space of the J transpose. And we can see that this is also satisfied if when this happens, when the rank of JQ is equal to the rank of JQ, add another vector to it. If the rank doesn't change, this means that x dot lies in the range of the joint space. And how you find the solution? You find the solution by left pseudo-inverse. The left solution is left pseudo-inverse gives you Jacobian transpose Jacobian inverse times Jacobian. Instead of using the usual solution, you find the pseudo-inverse solution. And the pseudo-inverse solution is not the exact solution, is the best approximation that you can get in terms of minimizing the norm of the system. Of course, I don't want to talk about this that much because under-actuated is very, very, let's say, advanced, and only our PhD student usually, I have a PhD student right now, and some master student that are working on the control methods for under-actuated system. And we should know that we have very limitations there. We cannot move as long as we would like to go. We don't have the right to go to any trajectory direction, and the final solution is found by the left pseudo-inverse. Left pseudo-inverse, we have J transpose J inverse by J, and J transpose J again is a M by M matrix, not N by N. M by M matrix that can be easily found by that. The interesting point is for redundancy, when we have redundancy. And you can see redundancy in the nature quite heavily. Let me talk about redundancy and then maybe close the session here, give the solution maybe in the next session. What is redundancy? If we have more actuators than required, and it is full in the nature. If you look at your shoulder, if you can look at your arm, not the wrist. The wrist is something else I will show you in the next slide. This is also very interesting. Just from the shoulder to the wrist, our arm has 7 degrees of freedom. 3 degrees of freedom in the shoulder, 3-degree direction, at least we can say 2 degree here, 2 degree here, or 1 degree here, 2 degree here. You see, we have this twist. This can be, and also the elongation here. Both of them are this direction, and at the wrist we have also all 3 direction. So we have usually, we can say 3, 2, 2 or 3, 1, 3. We have 7 degree of freedom, 7 degree of actuation. Of course, a hand needs only 3 position and 3 orientation. Why God considered adding another actuator to the system to become redundant in the nature? And we know that redundancy means the manipulability measure increases. We have 1 extra singular values here. Again, since we have worked on the shoulder manipulator in our robotic lab for years, of course, 20 years ago or 15 years ago, we have designed a parallel manipulator that resembles the shoulder manipulator, hydraulic shoulder manipulator. You can go to and read the papers about that. You can see that there are 4 different muscles acting this 3 degree of freedom. Not only this is redundant, but the shoulder itself is redundant, is redundantly actuated. We have 3 degrees of freedom at our shoulder, but we use 4 different muscle groups, as you call these muscle groups. You can see the names, the technical names for that. A bit more than that and stranger than that is our neck. Our neck, you can see that all the mammals' neck have 7 vertebrae, 7 bones, vertebra. 6 degree of freedom, but 7, again 1 degree of freedom. All, and giraffe has also 7. Don't look at the very long neck. The number of vertebrae are 7, 1 degree of redundancy. And more than that, amazing more than that is for the birds, when you go to the birds, this becomes 14 vertebrae. They need only 6 degrees of freedom to have a position and an orientation. But 14 vertebrae, as you see in here, all the names are given in the literature, you can find it. They are twice more double redundant, not 7, but 14. And also for the wrist. For our wrist. If you look at the wrist, the physiology of the wrist, you will see that there are 8 bones in here. 1, 2, 3, 4, 5, 6, 7, 8. And these 8 bones, we call carpal bones, for 3 degrees of freedom. Again, 1 plus twice. And each bone, you know that, it's not the bone, it's also the muscles which they include that. So you have more degrees of actuation than what you require. Of course, for more sophisticated creatures, for smaller and insects and maybe some small creatures, you don't see that many redundancy here. And of course, you can understand. If you look at that, you can imagine why birds need more degree of freedom. Why birds' neck should be more dexterous. Anybody can answer that? Even a giraffe has 7 vertebrae. Why? What about a bird? A small bird have 14 vertebrae at the neck. Why?
May I answer the question? Sure. Because they work with their head a lot. For example, a bird can pick a hole in a tree by its head, or go hunting, and they do lots of things with it.
You know, the nature requires, you know, the life of a bird depends on her neck, let's say. Not only hunting, escaping from a hunter also by neck, because the eyes and the neck should see and then escape from the hunter. Feeding, eating, watering, everything, because it doesn't have a hand, everything is by the neck. And the neck is double redundant. Double plus 2 redundant. And as you see, here comes the hand. What about the human? Human requires its hands more than the neck. The hands is the nature of a human being for writing and reading, learning, and using different tools. I say right now we don't use the tools by our hand. Usually we use our mind. We design the CNCs, and the CNC are doing the manipulation, the tools, but still we are using our hand to paint and to write. And that's why our wrists are very, very interesting. And if you look at your fingers and at your hand, this is most advanced. It has more than 21 degrees of freedom. Just your fingers to catch everything and to use your hand. So you need more than 7 or 6 degrees of freedom. Even for 6 degrees of freedoms, the God has designed a 7 degree of freedom structure, and everything you can see here or here or here. There are none of them are just single serial manipulators. The actuations are somehow parallel. You need to use some parallel manipulation design as well here to well understand what is going on here. So you see that this redundancy in the nature provides us some hint. If you would like to design some particular cases, you can have the redundancy. And what will be helping us? We can see that the helping is by the inverse solution. If you have a 6 by M matrix, I will repeat that in the next case, in the next session. But just to conclude, then we have infinitely many solutions for the inverse problem. If a bird would like to move the head from one point to the other one, it's not the only one way to do that. It has infinitely many. And this infinitely many helps her to use the most out of the actuator, very small actuators, very small muscles that are within the vertebra and within the neck. So we can use the most out of the actuation possibility that you have used. And you can again remember the cobra. It brings up the neck in a specific configuration, in a configuration similar to this configuration, Oh my God. Brings to a configuration that will provide you isotropic posture. Some posture which is very efficient in all the direction. And everything can be just simply seen by the Jacobian matrix. So we will go for the solution of the redundant manipulator inverse. Of course, simple example I will give in the class, but very, very effective, important solution would be given in the nature. And it is, again, very amazing. It is very difficult for us to calculate the inverse solution. But how this is working in the brain of a small bird, how to move the head in the direction to be alive, to get alive, and to get away from the predators. Very good. I hope that this has provided us with good motivation for the next classroom. It seems that the people are not very happy to change the class time, so we will go with the same class time at 7:30 to 9 in the morning. And of course, if there are some people who are not very easy at that time, they can follow the recorded videos. Thank you very much for being with me, but please contribute more in the class. I would like to know that everybody is listening and following me and not just opening their account and sleeping behind the scene. موفق مایت باشید. اگر سوالی هست در خدمتون هستم. من امروز today I don't have the regular office hour. I have a urgent meeting, so I don't have the regular office hour. If you have any question, you can come to visit me in the office hour on Tuesday.